Hey folks, welcome back to Combo Class. I'm your teacher Demotro, and today I gotta tell you some crazy things about what are known as pandigital numbers. Numbers that have all the digits in some base at least once. And before we look at why pandigital numbers are actually a fundamental, very important concept on the number line of any base you could count in, let's just first look at a few interesting examples of some pandigital numbers that happen to have some cool properties. Pandigital numbers come in various types. Typically, they're required to have all the digits between 0 and whatever your base's maximum digit. For our base, all the digits from 0 through 9 at least once. But sometimes they will be restricted to having the digits only once, in any order, but none of them appearing more than once. And there's various names that are given for that. There's not really a standardized terminology. I'm going to refer to them as my own term, which is minimal pandigital numbers, because it's the minimal digit length a pandigital number could have would be to use each of the digits exactly and only once. There's also zeroless pandigital numbers, which use everything from 1 to the maximum digit without having a 0 in there. And that's a zeroless pandigital number that uses some digits multiple times, but you could restrict them in a similar way and look for a minimal zeroless pandigital number that would just use the digits from 1 to your maximum digit without any zeros. One interesting type of pandigital numbers are pandigital prime numbers. This is the smallest pandigital prime number in our base 10 system, and this is the smallest zeroless pandigital prime. And we'll notice that neither of them are the type that I called minimal. They both have a repeated digit somewhere. And that's because in our base 10 way of writing numbers, it's impossible to have a minimal pandigital prime, zeroless or regular. And that's because any pandigital number that doesn't repeat digits in our base is basically putting the digits between 1 through 9, and whether or not we have a 0 in the mix or not, any ordering of these digits adds up to 45. And as we've seen before, if a number's digits add up to a threeven number, or multiple of 3, the number itself was threeven, and no threeven number bigger than 3 could be prime. In fact, when a number's digits add up to a multiple of 9 in our base, the number itself was a multiple of 9. So it turns out that any minimal pandigital number in our base, whether it's the zeroless type or the type with the 0, will have a digit sum of 45 and thus be a multiple of 9 and impossible to be prime. So the smallest pandigital primes of the zeroless and regular varieties need to include some sort of repeated digit. And speaking of divisibility traits, this pandigital number has a very interesting property known as polydivisibility. And in fact, it's the only minimal pandigital number that is polydivisible in our base. Now, what does polydivisibility mean? Well, it means that the first digit of the number, if that was a number of its own, is divisible by 1, which is pretty obvious. And the first 2 digits of the number, if that was a number of its own, 38 in this case, is divisible by 2. And 381 is divisible by 3, 3,816 is divisible by 4, and in general, the number created by just taking the substring of the first n digits of a polydivisible number will be divisible by n, up through this whole thing being divisible by 10. And not only is this the only minimal pandigital number with that trait in our base, if we asked for the minimal zeroless pandigital number with that trait, there is one which is that without the zero, and is the only minimal zeroless pandigital and polydivisible number in our base. And it turns out that in any base you could write numbers, there are a finite number of polydivisible numbers. Like in our base 10 system, there's exactly 20,457 numbers with that property, although not all of those are also pandigital. In fact, funny enough, the longest polydivisible number in base 10, this 25-digit monster, isn't pandigital. It doesn't have any ones or nines. Another interesting trait about pandigital numbers can be ones that have what's called persistence of a certain level. Unfortunately, the term persistent or persistence is used other places in math and gets confusing. There's something else called additive persistence and multiplicative persistence, which is a cool topic I want to cover in an episode someday. So for now, let's be clear that we're talking about a pandigital type of persistence. But this number right here turns out to be what we could call 4 persistent in terms of this pandigital persistence. And what that means is that not only is it pandigital, but twice it is pandigital, or if we multiplied it by 3, thrice it is pandigital, or 4 times it is pandigital. But the number we get if we multiply it by 5 isn't pandigital, so it's not 5 persistent, just 4 persistent. The maximum that a minimal pandigital number could have for pandigital persistence in our base. Although 4 is the highest level of pandigital persistence that any minimal pandigital number can have in base 10, if we don't require it to be minimal and allow repeat digits, we can achieve higher levels, like this number that's 6 persistent, where it's pandigital, twice it is pandigital, 3, 4, 5, or 6 times it is pandigital, although 7 times it isn't, otherwise we'd call it 7 persistent. And it's actually been proven that although there aren't any infinity persistent numbers, meaning that every number eventually has a multiple that isn't pandigital, if you pick any massive number of your choice, no matter how arbitrarily large it is, there will be a number with that level of persistence. So there's a 1 billion persistent number, a 1 trillion persistent number, and so on, but not an infinity persistent number. Now, if all of those pandigital, prime, polydivisible, and persistent numbers weren't enough P's for you, what about pandigital perfect powers? Perfect powers being the numbers like perfect squares or cubes that are some whole number raised to another whole number's power, with the exponent being at least 2. Well, the largest perfect power in base 10 that doesn't repeat any digit more than once is this number. And by making that condition that it doesn't repeat any digits, but that it's the largest, it ends up being one of the minimal pandigital numbers in base 10. So it's also the largest perfect power that's a minimal pandigital number in base 10. And the type of perfect power it is a square number, where if we take its square root, we get this number. Oh, no, wait. It's this number. Oh, wait, no, which? Oh, no, it's the same either way. 99,066. Speaking of square numbers, this zeroless pandigital staircase, this palindromic number that goes from 1 through 9 and back down, does turn out to be a square number. And in fact, it's the square of 111,111,111, the type of number I like to call a hypereleven, or you may see also called a rep unit or a generalized rep unit if you consider numbers just composed of ones in other bases. And it is interesting to look at the difference of these two, at least in terms of appearance, where one of them is just packed full of the lowest non-zero digit in the base, and if you square it, you get this other one that's packed full of every non-zero digit in the base. In general, in our base 10 way of writing numbers, at least in terms of appearance, the hyperelevens and pandigital numbers are sort of like on opposite ends of some scale, with a lot of other types of numbers in between. But what if we were counting in a smaller base, like base 2, binary? Well, in binary, where there are fewer possible digits, there's an even closer connection between the hyperelevens and the pandigital numbers. Here's a list of how binary would write the first non-negative integers. And here, to be the regular type of pandigital number, a number would just need to have the digit 0 at least once in it, and the digit 1 at least once in it, a trait that most of these numbers appear to have. In fact, to not have at least 1 0 and at least 1 1, you'd need to either be only composed of zeros, and any number of that form would simplify to just 0 itself, or you'd need to be just composed of purely ones, the hyperelevens of this base. So in terms of the general type of pandigital numbers that include zeros, they are precisely the numbers in this base that aren't 0 and aren't hyperelevens. But if we asked about zeroless pandigital numbers in this base, then it would be sort of the reverse of that. Because to be a zeroless pandigital number in this base, you just need the digit 1 at least once, and to not contain any zeros. So you'd have to be a hypereleven. So the hyperelevens are precisely the numbers that are the zeroless pandigitals in this base, or could be defined as precisely the numbers that, along with 0, are the non-pandigital integers in the base. And like I showed in an earlier episode, these binary hyperelevens are actually super important in math. Numbers that are written as just a string of ones when expressed in binary are 1 less than a power of 2. They're known as Mersenne numbers, and the ones of them that happen to be prime numbers also, known as Mersenne primes, are a special type, and the biggest primes currently discovered by humanity are all of that type, often called primes that are 1 less than a power of 2, or Mersenne primes, but I prefer to define them as the primes that are hyperelevens in binary. And we could also now see, we could define them as the primes that are zeroless pandigital numbers in binary, or the primes that are not the regular type of pandigital numbers in binary. Now, what if we tried to count how many pandigital numbers existed in some base? Well, there's an infinite amount of pandigital numbers in these bases, so let's start with the more digestible version of that question, which is how many minimal pandigital numbers exist in a base like base 2 or base 10, or another typical integer base 2 or greater. Well, here in binary, the only minimal zeroless pandigital number was 1 itself, because the rest of the hyperelevens weren't minimal. And the only minimal of the regular type of pandigital numbers was 10, because all of the further combos included one of them doubled, and we couldn't have swapped these digits to make 0, 1, because that would just end up being written as the 1. So in binary, there's one minimal pandigital of each of those types, zeroless and regular. What about in base 10? Well, we're not even going to encounter any of the regular pandigital numbers in the first billion numbers. But once we start hitting them, the minimal ones will be ways of rearranging the digits from 0 through 9. And in a way, we can see all of the possible permutations of these numbers as describing the total amount of minimal pandigital numbers, because if we made some permutation of these with the 0 at the front, it just wouldn't be written in our number, and we would have one of the minimal zeroless ones. And if we end up with one of the permutations where the 0 is tucked somewhere in the middle or the end somewhere, it'll be one of the regular pandigital numbers that includes a 0. So we should expect that the total amount of permutations of these 10 things, which is the number 10 factorial, somewhere in the 3 millions, to be the total amount of minimal pandigitals in our base. And if we wanted to know about for each of the individual types, well, there's going to be 9 factorial of the zeroless, and there's going to be 9 factorial, the ways of arranging those, times 9 places where the 0 could end up, because the 0 could end up in 9 potential spots if it wasn't at the front where it would vanish. So we're going to end up with 9 factorial times another 9 of the regular type, which add up to that 10 factorial total. And in general, for one of these typical integer bases, 2 or greater, the amount of minimal pandigital numbers of each type will be b minus 1, b being the base number, factorial amount of zeroless, and b minus 1 factorial times another b minus 1 amount of the regular. And when b is 2, either of those cases simplifies down to 1, which is why there was just one of each type there. So that's how to calculate how many minimal pandigital numbers exist in some base. But what if we asked a slightly more surreal question? How many pandigital numbers in general exist in some base? Now, a lot of people might say an infinite amount and quit there. But what if we tried to figure out the proportion of numbers in the base somehow that were pandigital compared to the ones that weren't? Well, one way you can try and compare proportions of infinite types of whole number is something called natural density. That's where you look at larger and larger stretches of the number line, scanning all of the whole numbers up to there, and seeing what proportion or percent of them fulfill some particular property. For example, if we wondered the natural density of the even numbers, well, that would be 1/2. Because as we go up the number line, we get closer and closer to the percent of numbers that have been even being precisely 1/2. And since it approaches a limit of getting closer and closer to half of the whole numbers having that property, the natural density of the evens is 1/2, and the natural density of the threeven numbers would be 1/3. But if we looked at the natural density of the square numbers, the whole numbers that are the perfect square of another whole number, we would actually find that for bigger and bigger stretches of the number line, the proportion of them that's been perfect squares shrinks. With a big enough stretch of the number line scanned, the percent of squares would get smaller and smaller past any tiny fraction you could imagine. and that approaches zero, meaning that the natural density of the square numbers is actually zero. So what about the natural density of numbers that are pandigital when written in some given base? Let's start by looking at binary, and we'll be looking at general pandigital numbers for this part that do include the zeros. And let's wonder, as we look at bigger and bigger stretches of how binary would write numbers, what proportion of them are pandigital at each point, and is there some place that that limit would converge to as we look at a big enough and bigger enough and biggest enough stretch of number line? Well, the only numbers that aren't pandigital here were 0 and the hyperelevens, which fall one less than a power of 2 and are as spread out as the powers of 2 themselves are. And the powers of 2 become scarcer and scarcer in a similar way to how the squares do. The powers of 2 also have a natural density of 0, so do the binary hyperelevens, and that extra 0 doesn't help them out enough to change anything, meaning that since the hyperelevens here plus 0 have a natural density of 0, the other stuff must have a natural density of 1, or what you could call approaching 100%. So in a strange sense, in binary, 100% of the numbers are pandigital. And while it might seem absurd to say that 100% of numbers when written in binary are pandigital, because we can see numbers that aren't, in terms of that logical metric of natural density, it does have a natural density of 1 for the general pandigital numbers there, or funny enough, a natural density of 0 for the zeroless pandigital numbers there, because those were just the hyperelevens. So under the logical metric of the natural density, we can say that 100% of numbers in that sense, when written in binary, are the general type of pandigital number, and 0% of numbers when written in binary are the zeroless form. So what about base 10? Well, in base 10, if we were looking for general pandigital numbers, in the first 1 billion numbers, we would have encountered none, but then we would start encountering some in the 10-digit and up range, and in the 10-digit numbers, it would still be a pretty small proportion out of all the 10-digit numbers that had all the digits once exactly, because a pandigital would need to be minimal at that size. But as we go up in digits, it becomes more and more likely that a number written in base 10 would have all these digits at least once. If you imagine a number with 100 digits, and imagine randomly picking all of the digit numbers, as if by rolling dice or something, you'd imagine it would be a lot more likely that you would hit all of the numbers at some point on your way to 100 than the chance that you would skip one and one of them wouldn't show up along the way. And what if you had a number with 1 million digits? Well, then it would have a tiny chance of not having each of these digits in it at least once. If you imagine rolling 1 million 10-sided dice, you would have to have none of them hit one of these numbers for the resulting number made from those numbers as digits to not be a general pandigital number. And if you were looking at a stretch of number line that ranged from 1-digit numbers to numbers that were 1 million digits, about 9/10 of the numbers there would be 1 million digits, which might sound weird, but let's have that sink in by thinking about smaller sizes of number. And if you compared numbers that were up to 2 digits, well, about 9/10 of the numbers between 1 and 99 are 2 digits. And if you compared numbers that are between 1 and 999, about 9/10 of those fall between 100 and 999. So every time you scan a new digit size, you are multiplying your range by approximately tenfold, or adding about 9 times more of numbers. Meaning that when we scan a big enough stretch of number line, the fact that no pandigital numbers showed up on the small scale and only handfuls of them showed up at the medium scale, well, when you zoom out, all those scales are tiny and don't matter in terms of the total natural density, since they become more and more common at a rate that approaches all of the numbers in a strange sense being pandigital, where if you were to scan the first numbers up through 1 million digits, although you would still be encountering numbers that weren't pandigital, you'd be closer and closer to 100% of the numbers you'd encountered having that property. We can say that for base 10 also, or for any regular integer base 2 or higher, we're gonna have 100% of the numbers in terms of natural density be a regular pandigital number, and 0% of the numbers be a zeroless pandigital number. Because when you get to those massive sizes, more and more of the numbers did contain a 0, so we can't call those zeroless, and the amount that have been zeroless will shrink down towards nothing. And we can take this further. If you were looking at a large enough stretch of number line, not only would most of the numbers be pandigital, but most of the numbers would have this exact string in a row in them somewhere. That might sound crazy, but if you imagine rolling 5 trillion dice, you can imagine that somewhere along the way, you'd encounter this string. And if you were at a big enough scale of number, it would be likely that somewhere in the average number, you have that string and all those strings and any string you pick. You can pick whatever favorite number you want. And in terms of natural density, 100% of numbers, or the average number if you were to try and somehow pick an average whole number on the way to infinity, will have your favorite number as a digit string within it. So pandigital numbers are kind of a paradoxical concept that makes us play with the fact that our human brains and number systems aren't really built to handle things on the big scale. On the small scale, pandigital numbers might seem like a rare occurrence, a strange, silly trait that just shows up in numbers once in a while. But if you zoom out, more and more numbers are pandigital, to the point at which, in some senses, 100% of numbers are. All right, folks, thanks for joining me to learn about the paradoxical trait that on some senses of measuring numbers, 100% of numbers have this digit string in them when written in our base. And even on a smaller scale than that, most numbers are pandigital, and most numbers aren't the zeroless pandigital, and all sorts of other... Okay, now we should get that part out. Let's see. Okay, 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 well, it's still lit, it's still lit. Okay. Okay. Thanks for coming to combo class.